That is correct. So, looking at today, velocity and other rates of change, we're going to start with the rate of change from geometry and how rates of change relate not only in specifically equations or functions, but how they can relate to real-world application and not even related rate problems. Like what we've been looking at is how rates of change relate in multiple variables, and that's where we got our related rate problems. But those kind of problems were specific because they were done with respect to time. Okay, you were talking about how the variables related with respect to time. Let's just look at rates of change without thinking about it with respect to time for just a moment, and then we'll go to some physics example. Now remember, instantaneous rate of change is still, if you think about a derivative, f prime of x is still the limit. I need this today, just trust me on this. The limit is h approaches 0. Who remembers the formula? F of x plus h minus what? F of x over h. You remember that formula? And that calculated the derivative for all x values, or it calculated the instantaneous rate of change for any x value. And you can even make it a little bit more specific. You can take that formula, and we know that we can calculate the derivative at a specific point. So using our definition of derivative, you can calculate the derivative at a point. So x equals a. If you were to actually take and go, okay, limit as h approaches 0 still, but f of a plus h minus f of a over h. That would not only calculate a derivative, but it would calculate a derivative at that x value, at x equals a. So that's doing two things. That's calculating the derivative and plugging a into the derivative at the same time. We don't do it this way. What do? We calculate the derivative with shortcuts, and then we plug in the a value. We definitely don't use the definition, but I need the definition today to prove some things. So I just wanted to remind you of what they are. Now, before we go any further, let's take a look at this first example before I get into some physics examples. Here's an example from geometry of how you can talk about a rate of change. It says this: find the rate of change of the area of a circle with respect to its radius f. But that's not supposed to be an f. So that's supposed to be an r. Okay? So typo. So find the rate of change of the area of a circle with respect to its radius r. Well, let's talk about this a second, because this is clearly not a related rate problem. How do you know it's not a related rate problem?
Because there's no time.
What'd you say, Canyon?
No time.
There's no time. It's not done with respect to time. What are related rate problems all done with respect to?
Time.
Time. Related rate problems are always done with respect to time. Here's a problem that's not a related rate. We're relating variables, but we're not relating them with respect to time. What does it say we want it done with respect to? The radius. So I want to relate the area of a circle with respect to its radius. So I'm not calculating dA dt. What am I actually calculating? dA dr. I want to find the rate of, I'm still finding a rate of change, but I want to find dA dr. That's what I'm after. So this is different from a related rate problem in that I'm not doing it with respect to time. I'm doing it with respect to a variable already in the formula. I'm going to find the derivative of the area of a circle with respect to its radius. I know I'm using a derivative because I say rate of change, and I told you unless I say average rate of change, you always assume what? You always assume the derivative, which is instantaneous rate of change. So when we say instantaneous, means derivative. I don't know how many times I'm going to say that, and still some of you are going to forget it. Okay? Hopefully nobody does, but it just never fails. Somebody forgets. Well, what's instantaneous rate of change mean? I don't know. Maybe derivative. Okay? So I'm finding the derivative of area with respect to the radius. Now, since I'm doing it with respect to the radius, I don't need implicit differentiation for the radius. We needed implicit differentiation before because it was done with respect to time, and time didn't even show up in the equation. Time was all relative. Okay? So time didn't show up in our equation, so you had to do every variable implicitly. So first of all, what's the equation that I'm trying to find the rate of change of? What's the equation that I actually want the rate of change of? How do you know it's a equals pi r squared? What gave it away? Area. Did it? Area of a circle? Okay. A equals pi r squared. That's our area formula for a circle. Now I want the rate of change for that. I want the rate of change with respect to the what? So I'm going to do A implicitly like I've always done, so that'll be dA dr. I want the derivative of area with respect to the radius. But when I go to the other side of the equation, what's the derivative of pi r squared? 2 pi r. And that's it. You don't need to multiply it by itself implicitly because we're doing the derivative with respect to the radius. So the radius is just normal. You just do normal differentiation with it. It's like dy dx. We never did anything.
dr over dr.
So if there was ever like an
Be dr or dr,
if
which
there
is
was
just
ever
one.
an x in the equation, it'd be dx over dr. We'd have to start doing
What now?
because it's not in terms of x. If there was ever an x in the equation, it would have to be
dx dr. Very good. That would be very true. If you had an x, if you had another variable in the equation to be done with respect to the radius, you would have to do those implicitly. I don't know if that's very practical, but that's what you would do. That is correct to say that. So we've got this. Part A is done. Go on to part B. Evaluate the rate of change, not just any rate of change, but the instantaneous rate of change when r equals 5 and r equals 10. So we could calculate how fast the area is changing at those given moments in time, which are relative to r equals 5 and r equals 10. So how would I write this notation? It's really important here. I want you to have some notation that you can use when you're doing the problems. So I'm going to have dA dr, the slash, that means when or at r equals 5. Just put that in the lower corner. I like the notation because it saves me some writing. It's a good way to write it mathematically. So dA dr is when r equals 5, then I just do what? Plug it into your derivative, 2 pi r. So 2 pi times 5, which would just be 10 pi. Now they didn't give us units, so since they didn't give us units, we could just talk about what is area measured in. If it's just units, let's just talk about units.
Squared units.
So it'd be units squared per what? What's r measured in? If they didn't give you any units, what would we just say?
Units.
Units. So it'd be units squared per units. And some people are like, would I simplify that? No. Because I want to know that the area is changing units squared per units. So at that moment in time, I would know at that moment when r equals 5, the area is changing 10 pi units squared per unit. At that moment, the area is going to change 10 pi units squared per 1 unit radius change, but that is only at that moment in time. It changes all the time. This is not constant. And if it was constant, it would be a constant over here, but we got 2 pi r, so I know it's not constant. Okay? What about the next one, dA dr? When r equals what? 10. So that'd be 2 pi times 10, which would be just 20 pi, same thing, units squared per units. And you don't want to simplify that because I want to know that it's units squared for the area and units for the, this is not dimensional analysis. You usually don't want to cancel units out like that if it's telling you something. The only time you cancel out when you're doing dimensional analysis is when you're trying to convert. Okay, and I'm not converting here. Okay. Part C, think about this now because we've really already answered that question. If r is measured in inches and a is measured in square inches, what units would be appropriate for dA dr? Inches squared per what? Inch, because it's dA dr. dA is measured in inches squared per inch. This would tell me, okay, the rate of change, it's going to change, the area is going to change inches squared per inch. That's telling me what the units are for each of the variables in that rate of change. That's why I don't want to cancel it, okay, unless I'm trying to convert. All right, any questions on how you can do a rate of change problem in something that you might actually use other than just y's and x's? Okay, because x's and y's are nice for math people, but unless it's in the real world, it doesn't make much sense. Okay, you might think of this. You might think of this kind of a problem if you're doing some kind of geometry and construction or manufacturing, and I'm trying to think of where you might do it. I can't think of anything off the top of my head, but trying to think of some kind of, are there waves in physics that are some kind of waves that are circular?
Oh, like sound
Radio
and
wave.
motion.
Are radio waves circular?
Radio.
Yeah.
Radio or circular? Okay, they extend out from a point and go out like a ripple.
Yeah.
Okay, so there you go. You can talk about it there.
Yeah.
Okay, cool. Alright, that's about all I want to say. Okay, don't go any further. Don't take me any deeper, because I might get lost. Alright, here we go. Motion along a line, particle motion. Okay? motion along a line, particle motion. All right, today we're going to start our physics talk, and I want to go ahead and the way we're going to do this, you will need your orange book for a little bit of it today. And so we're going to talk about physics, and I want to talk about what's referred to as position. We're going to start with position. So when I talk about motion along a line or particle motion, it has a name. It's called rectilinear motion. Okay, rectilinear motion. And it has nothing to do with proctology. Okay? Thank goodness, because it'd be a pain in the arse. Okay? All right? Rectilinear motion, motion along the line. Man, that's on video. I'm just going to make that one available on Moodle, not on YouTube. All right, rectilinear motion. All right? So motion along a line. Now, the way we're going to do this in calculus, we're only going to talk about one-dimensional lines. So it's going to be, and time's still going to be a component of this. And time's going to be, we're not going to know the exact time. Time's just relative. I mean, if we just know time exists, it's there, it passes. We can go forward in times and backwards in times, and we can talk about what happened in the past and what happened forward into the future mathematically. But we're not going to know what the time values are, and we're not going to worry about that too much right now. Tomorrow we'll get into specific time values. But what we're going to be talking about is the position along a line relative to time, okay, specifically related to time. We're just not going to know what that time is today. Now, there's two types of lines that we're going to talk about, a horizontal line and a vertical line. You can get into other types of lines if you go further into calculus. You can talk about motion along a curve. You can talk about motion along a line that's not horizontal or vertical. You can talk about motion along a function. Okay, but we're not going to really worry about that. We can talk about motion of a fly that's moving through space. And that's really complicated. So we're going to make it very simple, and we're just going to talk about motion in a horizontal line and vertical line. And that's where you start in Calc 1. Calc 2, you get into more multi-dimensional. You can even get into motion in three-dimensional space. Okay, so that's not where we're at. So we got to start with this, so one day you can get there if you go further. So when I talk about motion line, we need to first of all start with how we're going to define its position. Position, when we talk about position in this class, we're going to talk about it as a function s, and that function s is going to be a function of time. So from now on, when I talk about position, we're going to say s of t is position, because s will be a function of time. So s is a function of time, so we're just going to call it s of t, position. So whenever you hear me talk about position, you're going to say s. S is position. S, position, is calculated based on time. Now today, like I said, we're not going to know what that time is right now, but tomorrow we will. Okay? So S, its position is calculated as a function of time. That's how you're going to calculate position. So tomorrow I can say I want to know the position at t equals 2. Well, if you got your position equation, you'll just plug 2 in for time and you'll calculate your position. For example, tomorrow, if I had S of t was equal to t squared plus 3t minus 4, tomorrow you'll be able to say, okay, if I want the position at 4 seconds, I just plug in what? 4. So it'd be 4 squared plus 3 times 4 minus 4, 16 plus 12, 28. 28 minus 4 would be 24, right? So you know its position after 4 seconds, or 4 minutes, or 4 hours, whatever time is. Again, it's all relative. Okay? So the position after 4 whatever is 24. Now, the thing that I want to say to you is that in calculus, position does not always have to be positive. See, in 9th grade in physical science and in geometry, they've kind of created this idea that everything's always going to be positive. That's why in physical science in 9th grade, you have been told in 9th grade that when the acceleration is positive, you're speeding up. And you were told in 9th grade when the acceleration was negative, you're slowing down. And that's true some of the time. It's not always true. In fact, it is possible for your acceleration to be negative and to still be speeding up. And we need to talk about why that is. And that's what we're going to get into today. So, with that, where does the negative come from? I'm about to introduce to you where that negative comes from. So far we know position is S of t. So what I want to introduce to you today is a very important concept in calculus, which also overlaps into physics, and that is displacement, the difference between displacement and distance. So what I'm going to do for you is I'm going to make a number line here. We'll just let these rows represent the tick marks on the number line. So you're going to be 0, you'll be the origin, you'll be positive 1 because we'll look to your right, because you guys are looking this way and right is this way, correct? Okay. 1, 2, and you'll be negative 1 and you'll be negative 2. So we're going to talk about displacement. What is displacement? Well, let me start with this. If I started right here where Joe's at 0 on the number line, and you were going to count my distance traveled. Each tick mark, don't worry about the time, just count how far I travel, okay? Ready?
1, 2, 3, 4, 5, 6, 7, 8, 9.
How far did I travel?
10.
I traveled 10 units, okay? That is my total distance. That's what you would talk about in geometry. That's what you would talk about in 9th grade physical science. But it is not what we're going to talk about today. Because more importantly, it's not how far we traveled, but how far we've been displaced. Displacement is different from distance in this way. See, my total distance that I just traveled was 10 units, but my displacement is 0. Let me explain. If you get on the treadmill today and you were to run an hour, and I use Billy for an example, and I'll use Matthew Sierra since he still runs. Okay, I wouldn't use Canyon, but so Canyon doesn't run anymore. He walks around a lot. He's spazzing out all the time. Ah, I need to do a program. Okay, so Matthew gets on the treadmill for an hour today. Probably runs 7, 8 miles. That's the distance he traveled. He traveled 7 or 8 miles, but he displaced nothing. His displacement is 0. Why? Because he didn't move. Okay, he might have traveled a distance of 8 miles, but he didn't move anywhere. Okay, he's actually, where he started is where he's finished. He didn't go anywhere. Okay, he didn't move. In fact, you can go watch him for an hour, and you're going to say, he's not moving. Okay, he might be going 8 miles, but he's not moving anywhere. Same idea on the track. If you go to the track and you want to run a mile, how many laps you got to run? 4, just testing your knowledge of the sport. 4 laps to run a mile, right? Actually, 4 laps and about 9 more meters, but we'll go with 1,600 meters as a true mile, even though it's 1609. But if you go, 1609.24 to be exact, but if you go a mile, most of you think of running the mile, you go 4 laps on the track, right? So you're actually going to run a mile, and everybody would say, I did work. Okay, I'm not even going to get into that whole discussion. Okay, but I did work. I worked for a mile. I ran a mile. I go home and I talk about I did run a mile, but you displaced nothing. So actually, in calculus, you've technically done nothing. Okay? If you run a 2 mile, you'd run 8 laps. Okay, and that's an event in track and field. So Brandon Carls, when we were in track one year, he wanted to get a track and field t-shirt that said, Perm Track and Field Distance Team, and put on the back, displacing 0 has never been so hard. Well, it's kind of cute because it's true, because a track and field athlete, if they run a lap race, a 400 and 800, a mile, or 2 mile, their displacement is always going to be what? 0, because displacement is defined as this. You ready? Displacement is defined as final position, which a lot of people will call the end. Your end position minus the what? Initial position, which a lot of people call the what? Start. Now, mathematically, I'm going to give you a formula for this in just a second. And since we said position is S, think about it on a number line for just a second. If I have a number line, and I'm not going to label it, but I'm just going to say, here's the particle. The particle could represent anything, okay? And here is S of t at time equal to t. I just don't know what the time's at right now. And that particle could represent any object. It could represent a person walking, running, a football player running on the field. It could represent, that would actually be a good example because you can see how it could be, you know, you lose yards, you gain yards. So that would be kind of a really relevant example of moving left and right. You could think about a car driving down the road, as long as it's going east and west or north and south. You could talk about an object being thrown in the air as long as it's going up or down. You could talk about a train on the tracks. okay? Any object moving left, right, up, or down. And we're going to talk about only motion in a straight line. So that's going to be a vertical line or a horizontal line only. We're not going to have a line with a slope other than 0 or undefined. So motion in a horizontal line or a vertical line. So if you talk about its position, and let's say that object travels a certain amount of time, and let's say it goes to the right, and it stops. How much time took place? You don't know. I just know that if this, no, you can't say t because this was time t. How much time took place?
Sometime t plus t.
Let's call this, first of all, let's call this delta what? Delta t. So if delta t took place, and this right here is t, time t, what would this be? T plus delta t. So what would its new position be? At time t, it's s of t. What would its new position be if the new time is t plus delta t? S of t plus delta t. Now, assuming that this one's the start and this one's the end, the way we're going to calculate displacement then is the change in s, which we will call displacement, is what?
Final minus initial. T.
What is the final here?
T plus delta t.
Now that's the time, final position.
S of t.
S of t plus delta t minus s of t. This calculates displacement. I need that. I need that to get into velocity and acceleration. So this calculates displacement. Now, here's the thing I want to explain. So I go back to my example where I ended here and I traveled a total distance of, what was it, 8 or 10? How far did I travel? 10 units. I started by Joe and I'm ending by Joe. What would my displacement be? 0. Now, watch me here. Don't care about my distance now. I just want you to calculate displacement. Don't even worry about my distance. Who cares about my distance? And I stop here. What's my displacement? Here's how you knew that. I'm at a position of 1. That's my end position. My start position is 0. If I go 1 minus 0, I get a displacement of positive 1. Now, I want to tell you, the positive and negative now matters, and this is where you get into the things that they told you in 9th and 10th grade were not false. They were correct because they were assuming everything was positive. They just left out some important details. Okay, they left out the whole negative side of things. Okay, they just didn't want you to get too negative about it. Okay, so we need to talk about what happens when that negative is introduced and how it changes velocity and how it changes acceleration and how you interpret those. Okay, so my displacement, when I say it's 1 minus 0, I get the answer is positive 1. What that tells you is that I've been displaced. I have moved 1 unit to the right of my starting position. My end position is 1 unit to the right from my starting position. That's what displacement is. It's how far you displaced from your original position. That's all you're measuring. Displacement is measuring. And that's still a distance, but sometimes that distance can be what? That distance sometimes can be 0, because it's not truly distance anymore. It's what? Displacement, which takes into account positives and what? Negatives. Now, what happens if I do this? What's my displacement now? Negative 2. What does the negative tell you? The negative tells me that I've been displaced 2 units to the left. Now let's just go ahead and clarify. Positive in calculus, when we talk about physics types problems, okay, when we're dealing with physics, positive will always be to the right or moving forward. That's how they relate. So whenever we talk about a positive distance or a positive displacement, we're talking about moving to the right or moving forward. If I talk about a negative displacement, we're talking about to the left or back. So we can either move forward or move to the right, or we can move left, or we can move back. If you talk about vertical motion, it will be up, or if positive, will be moving up. Negative will be moving down, okay? All right, and moving forward would be up still, and moving back would be moving down, okay? But usually we just say up and down when we relate to vertical motion. When we go left and right, we sometimes say forward is right, back is left, okay? So, knowing that this can be negative or positive is very important because that leads into our next concept. Okay, now I'm not going to do a bunch of displacement problems. How many think you can figure out displacement on your own? You just take what? Final minus initial. That's not very hard. Okay? I'm just going to take my end position. If you don't have your end position, which we're not going to have, so I'm going to give you the position equation tomorrow, you're going to have to calculate your end position by using the position equation by plugging in the time that you want. So if I want to know the displacement in the first 4 seconds from 0 to 4, you're going to have to figure out S of 0 and S of 4. And you're going to have to take your end position minus your start position. So you're essentially going to take S of 4 minus S of 0 and calculate your displacement that way. If it's positive, you're going to say it moves to the right this many units. If it's negative, it moves to the left. If it's 0, you're going to say, I ended where I started. Okay? Now, that leads into instantaneous velocity. I want to get there. How are we going to get to instantaneous velocity? Because what you should know from physics is, or 9th grade physical science, and I'm not even going to assume you had physics. I'm going to make the assumption you haven't even had physics. How did you calculate velocity? What do you know about velocity? Velocity is the rate of change of what? Distance over time. It's the rate of change of position. But the way we're calculating position is we're not calculating position as total distance, we're calculating it as what? Displacement. So when I talk about average, let's talk about average velocity first. Average velocity. Okay? Now, to do average velocity, that is spelled so goofy. Let's do it right. Average velocity, we'll call it delta V. Okay, whenever we do average, we'll use delta. Because we know we're not talking about an instant in time, we're talking about over time. An interval of time, if you will. Okay, it happened over an interval of time. So delta V would be, you said 9th grade, it's distance divided by time, but what are we using to calculate distance? We're not talking about, we don't want to assume everything's positive anymore. We don't want to know distance can be positive or what?
So delta S.
So it'd be delta S over delta T. So it's going to be your change in position over your change in time, and your change in position is displacement. Everybody say it. Change in position is what? Displacement. Okay? So when we talk about change in position, we're talking about really displacement. So this calculates. Now, since this can be negative or positive, what can be true about velocity now? Negative or positive. And since this, when it was positive, it meant it was displaced to the right. When we go to velocity, it means it's going to be, now we're talking about movement. Velocity is talking about how fast it's moving. So if this was talking about how far it was displaced to the right or left, now it's going to be talking about not how far, but what? How fast it's moving to the right or left. So now it's going to be talking about really velocity as a vector. And if you know anything about vectors, vectors have magnitude, which means how much, how fast, the size of something, but it also has direction. So when you're talking about velocity now, we're going to say, hey, velocity can be negative or positive. When the velocity is positive, we're really going to be talking about when it's moving to the what? Right or forward. When the velocity is negative, it's going to be talking about when it's moving to the left or back. Everybody say it with me. Velocity is positive, we're going to be talking specifically about when the object is moving what? To the right or forward. When the velocity is negative, we're going to be talking specifically about when the object is moving left or back. Positive velocity would also be up. Negative velocity would also be down. And that really brings up a key point here. Velocity describes motion. Write that down. Velocity, that's like so important. It's like one of the most important things you grab today. Velocity is always what you use to describe motion. People are like, well, what about position? Position doesn't describe motion. Position describes position. Position just tells you where the object's at. It doesn't tell you what it's doing. To tell you what it's doing, I need velocity, because velocity will tell me how fast it's going in which direction. Because it has two components to it. Because it's got that positive and negative now. So do you see where the negative is going to come from now in velocity? Because we're using displacement. Now, here's what we got to get to. I don't care about average velocity. And I know in physics all you care about is final and initial. I don't care. Okay, that's not, this is calc. Welcome to my world. We care about the velocity at any moment. So how am I going to take this? You ready? This is where everybody gets excited. How am I going to take this and go from average to instantaneous? Well, I'm going to think first of all is that change of V. We know what change of S. How did you calculate change in S? How did you calculate displacement? S of T plus delta T minus S of T over delta. Now, over what? Delta T. Oh my gosh, this is starting to look like something that's familiar. What is this?
It's the
Derivative thing.
No, not the derivative yet. It's the slope of the, no, not the slope of the tangent yet. It's the slope of the secant. Look at it. Our slope of the secant was f of x plus h minus f of x over h. The only problem is h is not h anymore. H is what? H is delta t. Okay, our h values are delta t. Our f equation is not an f equation anymore. It's a what? S equation. So it's not f of x, it's s of t. Now, this is still average velocity. I'm still calculating average velocity. How can I change this over? What can I do to it to change it from an average to an instantaneous? Yeah.
Change delta t.
Yeah. Come on, think. First thing we did in this class for calculus. Limits. What can you do to change this? This is calculating an average over a time interval. How can I make this a derivative? What? I'm going to take the limit as what?
Delta t.
Delta t usually would be h, but now it's delta t approaches 0. If I let delta t approach 0, I'm going to not talk about the time over an interval. I'm letting delta t approach 0, which means I'm going to eventually get to a moment in time. Now I'm not going to be talking about the average velocity. I'm going to be talking about the velocity at an instant. So I'm going to let delta t approach 0. Now look at this. Ready? This is where it gets fun. T plus delta t minus s of t over delta t. I think this is so cool because this proves why this is true. Look at this. This is now a derivative. But the question is, of what? I'm telling you right now, guys, you just went from average velocity to no longer average. This was average, this is instantaneous velocity. So we're just going to call this, by the way, we call it instant velocity, we call it v of t. We don't call it delta t anymore, we call it v of t. Because this is going to calculate the velocity at a given moment in time. Do you see the difference? Delta v calculates the velocity over time. This calculates the velocity at a specific moment in time. So this is no longer average velocity, this is instantaneous velocity. But let me ask you, if instantaneous velocity is a derivative, what is it the derivative of? Look in this formula. What is it the derivative of?
The change in position.
Nope. Not change in position.
It's the rate of change.
It's the derivative of position. Think back to your formula. F of x plus h minus f of x. Remember I told you? I did this a couple weeks ago. We did a multiple choice question on the last test related to it. And I said, anytime you want to look at the formula, f of x plus h minus f of x over h, you always know what you're taking the derivative of because it's whatever's right there. If this is the derivative formula, is this not the derivative formula? Are you not staring at the derivative formula?
Yes.
Instead of f's, you have s's. Instead of h's, you have what? Delta t's. Okay? And instead of x's, you have t's. Okay? So this is the derivative formula. Agreed? So if this is the derivative formula, you should be able to look right there and tell you what you're taking the derivative of. You're taking the derivative of position. This is huge because what I've just told you is that if I give you position, write this down. If s of t is position, if you want to find velocity, what do you need to do?
Find the derivative of position.
The derivative of position is velocity.
So that is the derivative of velocity.
I have a question.
Right.
Spoiler.
Okay? So, the derivative of position. Now, this makes sense to me. Like, totally makes sense. Watch. Use a different notation. Don't use s prime of t. Use what we've been using for related rates. What would it be? D what? ds dt. Think about it. Change in s, change to ds when you took the limit as delta t approach 0. Change in t, change to dt. It's no longer change, it's instantaneous. ds over dt. Isn't this distance divided by time? ds divided by dt, isn't that position divided by time, which is velocity? So that should make, it's not average anymore, it's instantaneous. So, what you've just learned, ladies and gentlemen, is that the derivative of position is velocity. Now, what does a derivative calculate still? Go back to generic. What is the derivative really calculating? It's calculating the rate of change, which is the slope of the tangent line. Go to the example here. I love this stuff. So good. Find the velocity of a race car. The figure shows the time to distance graph. What does this figure show? Time to distance. So what's on the x-axis? Time. Let's give it a unit. It looks like it's going to be seconds, doesn't it? I haven't even read the problem, but I think it's seconds. It says, the figure shows the time to distance graph of a particular race car. Find the average velocity of the car from t equals 4 to t equals 7 seconds. So it's in seconds. Now, this is in seconds. Do you think a race car is traveling 50 miles in seconds? So what do you think? What do you want to go with here on the one? This is distance, which, by the way, we don't call it distance anymore. We call it what?
Displacement.
True, but position, which is related to our displacement. Displacement, guys, is not position. Displacement is the change in position. Okay, remember change. Final position minus end. Final position minus start position. So displacement is the change in position. All right, so distance to time graph. All right, so let's look at this. It says find the average velocity. Oh gosh, really? They're going to ask us that. Find the average velocity from 4 to 7. So here's 4. So what we're saying is at 4 seconds right here, what's the velocity? Or sorry, not the velocity. What's the position? 100 what? What do you want to use, meters or feet? Let's do meters. I like meters. This is the meters. So we know S of 4 is 100 meters. So after 4 seconds, it reaches 100 meters at its position. All right? It wants us to find the average velocity from 4 to 7. So we got to also find its position at what? 7. Now tomorrow you'll have an equation. You won't be reading it off a graph. But it's easy to read off a graph, right? Just tell what the point is. So at 7, we're in a position of what? 300 meters. What are you wanting to calculate when you calculate? Tell me geometrically what you're calculating when you calculate average velocity. No, you're going too far. Yeah, you're doing change position over time, which is the slope of the what? There you go, slope of the secant line. It's the slope of the secant line. All you're calculating, so 9th grade, all right? So if I want to calculate average velocity, which is delta V, I'm just doing 9th grade slope. Okay, so I'm going to go final minus start over the change in time, which, how much does it change from 7 to 4? 3 seconds. So, and you can write 7 minus 4 if you want to actually show that. So it's going to be 200 over 3 meters per second. So there it is. That's awesome. We could have done that in 9th grade. I feel so cool. No, that's not really cool because we can do that in 9th grade. What we want to be able to do is something more interesting, which is instantaneous rate of change. So find the instantaneous rate of change at t equals 4 and t equals 7. Now I'm not asking for the slope of the secant. What am I asking for? Because now here's what I want you to get. I want to make the connection now. This is still time, okay? What I want you to make the connection is at 4 seconds, I want to calculate the instantaneous velocity. What did I just say the instantaneous velocity was? It's the derivative of what? That's what. Velocity is not the derivative of velocity. What did I say instantaneous velocity was the derivative of? Position. This red graph is the position graph. So if this red graph is position, its derivative, which is slope of the tangent, is velocity. So that's how I know to look at the slope of the tangent. I know if I want to find the instantaneous velocity here, all I got to do is look at the slope of the tangent, which is the derivative of position. So guys, when you look at the slopes for position, you're really looking at what? What are you really looking at when you look at the slopes for position?
Velocity.
You're looking at velocity because velocity is the derivative of position. That's the connection you got to make. Position, the derivative of position is velocity. And since we know the derivative is the slope of the tangent, every time you look at slopes on a position graph, you're really looking at velocity. So where the slopes are positive, answer me this, Batman, where the slopes are positive, the velocity is going to be positive, which tells me that the particle's moving which way?
Right.
Right. where the, don't worry about up. Oh, if we're doing vertical motion, yes. Where the slopes are what? Negative. If the slopes are negative, the particle or object is going to be moving left. Where the slopes are 0, the object's not moving.
More constant velocity.
Yes, it is. It's going to be so much like that. 7. Now, what do you need to be able to confidently say? Ready? What do you need to be able to say with confidence what the velocity is at 4 and the velocity is at 7? How would you figure out the velocity at 4 and at 7 from this graph? How would you find the instantaneous rate of change at 4 and 7? You'd figure out the slope of the tangent line, right? But what's the problem? No, it's not that we don't have any rules. What's the problem with finding the slope of the tangent line looking at that graph? What's the best you're going to be able to do? You're just going to guess. You're going to approximate. You're going to look at it and approximate. You might get it, you might not. You might get close. You should get close. What do you actually need to find the exact velocity at 4? You need position. Because if I had the position equation, what would you do to get velocity? If I had the position equation, what would you do to get velocity? You would take the derivative of it, and then you could plug in your 4 and your 7. But I don't have the position equation, so guess what we're stuck doing? Approximating. So here's what we're going to do. We're going to look at it at 4, draw in a tangent line where you think it should go, and then you're just going to look at it and say, ooh, these go up by 50, these go over by 1, so let's look at it. It looks like it goes over 50 right 1. So what would you say approximately is the velocity at 4 seconds?
150 per second.
I'm actually going to write it S prime of 4, which is V of 4, is approximately, what would you say?
50 meters per second.
You would say approximately 50 meters per second. If I wanted to know the instantaneous rate of change at 7, I know that's the derivative of position now, which is calculating the slope of the tangent line, which really calculates V of 7. And what would I say that one is approximately? That one doesn't go up 50. It goes up a little bit more than 50. What would you say? 100 would be 2 of them. Maybe 75? 75 meters per second? So you could approximate the derivative. That's the best you can do. Okay? Just to mention speed real quick. That was good. You guys are grasping it. So, what is the derivative of position? Velocity. Derivative of position, velocity. I want to finish this up real quick. I'll do example 3 tomorrow. Speed graph. Just write this down. Speed. When you look at odometer, you're looking at speed. Now, speed is not worrying about if it's positive or negative. Speed is simply, who knows what speed is from physics?
It's just a
Relative
scalar.
It's a scalar quantity, which means it doesn't worry about if it's positive or negative, so it's just velocity without the what? Without the sign. So here's how we do it in math and calculus. We say speed is the absolute value of velocity, and that is so important. I know it doesn't say much to you today, but it will later. Speed is the absolute value of velocity. Very important. It's actually going to help us calculate total distance. Okay, now I'm going to skip example 3, and I really at least want to give you the acceleration equation. And the acceleration equation is very similar. Then we'll come back. Your homework is Orange Book. You have Orange Book homework tonight. You have quick review, and then you have 1 through 7. It's on Moodle. And then you have your derivative review due Thursday. Acceleration, really quick. What is acceleration the rate of change at? You did average acceleration. What was it the rate of change? Acceleration is the rate of change of what? Velocity. If you know physics, you know it's the rate of change of velocity. Now you can go through, watch, you can go through the same proof for this. You go, acceleration is v of t plus delta t minus v of t over delta t. And then you'd say, oh sweet, I got the slope of the secant again. What could I do to get to instantaneous acceleration? Take the limit as delta t approaches 0. Of v of t plus delta t minus v of t over delta t. It's no longer average acceleration, it's instantaneous acceleration, which proves that acceleration is the derivative of what? Velocity. Now, here's what I want you to relate before you leave today. Know this. If that bell rings, you listen. I'm bringing you hot. We're going to do hot dogs. So, position. What's the derivative of position? Velocity. Hang with me. I'm almost done. One more statement, right? Now, if position, the derivative of position is velocity, what's the derivative of velocity? Acceleration. Now, hold on. This is huge. I'm about to tie them all together. Ready? If velocity, derivative velocity, acceleration, that's the second derivative of what? That's what I want. If you start with position, one derivative down is velocity, two derivatives down is acceleration, and we'll get into that in a lot of detail tomorrow. Because tomorrow, all we're going to do is practice this thing. There we go. I got through it. Now we can just do problems tomorrow. Homework's in the orange book for tomorrow. It's due tomorrow in the orange book. And it's only I think it's 17 problems.
Nice. All right. See ya.
Okay, see you later. What's for lunch?
Oh,